So, if we know all this stuff, and now we know the mass, we can do stuff. Because if you see a planet transit go in front of its star, that basically means we're looking at it sideways. So that means that the velocity we measure is the actual velocity of the star. So the mass that we calculate is not a lower limit, but it is the actual mass of the planet that we calculate, right? Because this angle is roughly 90 degrees. So if we know the actual mass of the planet, not just the lower limit, but the actual mass, and we know the size of the planet, we can determine the density. And that tells us something about the composition of the planet. So let's go to a planet. So we have this star, Kepler 452. You see these numbers, the mass slightly more than the sun, radius slightly more than the sun, luminosity slightly more than the sun. That works like that. I mean, if you have a more massive star, usually it's bigger and usually it shines more, right? So we measure the luminosity, we find this, and then there's a small dip, as you can see, 196 particles per million. That's not a lot, but okay. And from that we can find that the radius of the planet is this. We know the period, look, 384 days, 85. So slightly longer than our year, not bad. And the distance, slightly more than our distance. We assume this albedo. We find this, sorry, that should be a Q, equilibrium temperature. And then from radial velocity methods, very precise measurement. Still a bit in doubt if it's in actual detection, but still we want to look at what happens now. We find this mass of the planet and this density. And if these numbers don't mean anything to you, let's compare them to the Earth. So for the Earth, you can see this planet is, well, quite a bit bigger than the Earth. This is the radius of the orbit, so slightly farther away from its sun. This is the equilibrium temperature in Celsius now, -8 for that planet, and for the Earth it's -18, by the way. We don't notice that because we have a normal greenhouse effect, which adds roughly 30 degrees. So the average temperature on Earth is roughly plus 12, 13, 14 degrees or something like that. And we're adding to that now, and that's not a good thing. So the mass of the planet, 5 times the Earth, so that's much bigger, right? That's much more. And that means the gravity is almost twice as much as on Earth. So if you would stand on the scales there, your weight would be almost twice as much. And then we look at the density, and you see this density is slightly more than the density of Earth. So we expect something like this. So what we call, well, basically a super Earth, slightly more massive, bigger. It might be, well, it is in the habitable zone of the Sun-like star. Habitable zone means that the water, well, if there is water, it can be in a liquid form, right? So if there are temperatures between 0 and 100 degrees, we expect liquid water to be there. And liquid water is important, of course, we know that's important for life. So, but also, if you have liquid water, it evaporates, you can have clouds, and you can have a runaway greenhouse effect like Venus. Because the temperature that we calculated is just a calculated temperature, it's not measured, right? It's just something that we expect, and if it's something else, we have to explain that. Because of the strong gravity, we also expect more tectonic movement, more volcanoes and stuff like that. And that's usually not good for the environment, but okay. We get an idea of this super Earth. So let's go back to the news messages we saw at the start and zoom into each of these, right? So the first one was this, KELT 9, and KELT is a funny name, but as you can see below, KELT is just an abbreviation of this, the Kilodegree Extremely Little Telescope. Here it is. It is actually just like this. We have 2 of them, one on the northern hemisphere, one on the southern. And they do these observations, so, well, nice, but as you look at this, let's see, the radius of the planet, almost twice Jupiter, pretty big. The mass, more than twice Jupiter, and if you calculate the density, that means the density is half Jupiter. So this is much bigger, and if the planet is twice as big, with the same density, you expect the mass 2 to the thirds, 8 times as much. So you can understand that the density is less, and basically this density is roughly the same as Saturn. And Saturn will float. If you have a really huge pool, really huge, you can float Saturn. Okay, but the density is lower than water, and the same as this for this planet. So again, 36 hours is the time it takes for the planet to go around its star. which is really, really short. And of course, then we find this equilibrium temperature, so that's insane, right? So what happens if you heat liquid or gas to this temperature? It swells. And that's why we have this huge radius, almost twice Jupiter, because its atmosphere is swollen up, right? It's really big. And also because it's so close to its star, that basically means the rotation around its axis is slowed down to the speed that it's always with the same side to the sun. Like the moon is to the Earth. We always see the same side of the moon because it's tidally locked. Its rotation has slowed down so that it rotates once around its axis while it rotates around the Earth. And if you do that at the same time, you always show the same face. And this planet does the same thing with its star. So basically means the front side is really hot, its back side is slightly less hot, but it's still hot. And probably, because it's so close, on the back side of the planet, from the star, the atmosphere is blown away. So it might look like this. This is an official NASA animation, so it must be right. But it might look like this. And there's something else, except for the planet basically evaporating and, well, dying slowly. There's something else. You can see the star rotates in this direction, where the planet goes in that direction. And that's strange how that happens. Usually everything turns in roughly the same direction. But you can also see that this sun, or this star, is stretched out in this direction because it rotates also very fast. And where it's stretched, the temperature is slightly lower, and where it's flattened, the temperature is slightly higher. And this planet moves over the poles, right? It moves in a polar orbit, so over the North Pole, equator, South Pole, equator, and back again. So basically in a year, which takes 36 hours, in a year it has 2 summers where it's really hot, and 2 winters where it's almost really hot, right? Because it's still very near the star. So to call this an ultra hot Jupiter is a very good name. Okay, so this is one of the examples.